Hi, in this video, we are going to see how to find the probability mass function of a single discrete random variable. So what's the difference between the discrete and the continuous random variable? So by definition, given a random variable x is a discrete random variable if the range of x is countable set. That said, we can list the element in the range of x. Formally, we can write Rx as x1, x2, x3 up to xn, where xi are possible value of the random variable. So that said, if you have, let's say we have a set x, so if you have something like this, if you have the set x equal to 0, 1, 3, 4. In this set, you can clearly see that we can count all the elements in this set. So this is a discrete random variable. However, if you have a set S, which is something like this, maybe 0 to 7, this is a continuous random variable because you cannot count the element in this set. So basically, we are going to do another video where we explain, we will be finding the probability mass function of a continuous random variable. But in this case, we are focusing on the discrete random variable. So that is what is a discrete random variable, and the difference between the discrete and the continuous random variable is that we can count element of the set of interest in the discrete case. So what's the probability of an event? An event is a outcome of an experiment involving a random variable. So for example, if you throw a six-sided dice, you can get as possible a set of all possible outcome for the six-sided dice is you can get out 1, you can get 2, you can get 3, you can get 4, you can get 5, you can get 6, right? So the probability of getting x equal to 6, for example, equal to 1 over 6. So if you denote by x if you denote by x the event of getting something from the set of possible outcome, which is the set S, the probability of getting 6, for example, is 1 over 6. The probability of getting 5 is again 1 over 6, because all of them we have the same chance of getting one specific outcome. That's why we say the probability is 1 over 6, because we have the 6 possibilities and we can always get one of them. So that's the 1 over 6. So they have the same chance of occurring. So we pick for example, a second example here. If you toss a fair coin twice and if you denote by x, so this is very interesting. So if we denote by x the number of head observed and the sample space, S is the sample space. So because you are tossing a fair, we are tossing a fair coin twice. So if you note that this is the first toss and this is the second toss, so you can get head on the first toss, then head on the second, or you can get head on the first toss and tail on the second, or you can get the tail on the first toss and head on the second, or you can get tail and tail, right? That's the set of possible outcomes. So that's how we got this set. So that's the set of the possible outcome, which is the sample space. Now our variable of interest is the number of head that we observe. So this is our variable of interest. So x will be, because we can only get if you the number of head that we observe. So we want to say how many head we observe on this experiment. So for the first time, you can get head and head. So in this case, you get 2 head, right? In this case, you get 1 head. So in this case, so if you're here, x equal to 2. For this one, x equal to 1. And for this, x equal to 1 again. And this, x equal to 0, right? So the set of, if you denote by x the number of head that you observe, so the set of x will be, we can get either 1 head or 0 head or 2 head, right? So what's the probability of getting one head? So what you see is how many times you have 1 head here. So this is 1, we have 1 head here, we have 1 here, So the probability of getting x equal to 1, which denotes the number of head that you observe, is you count how many times you have the head in the sample space is 2 times, so that's why we get 2 over 4. You do the same thing. What's the probability of getting 2 head? So you can only get 2 head in this case, so that's why we have 2 over 1 over 1 over 4. The probability of getting 0 head is, in this case, you don't get the head, it's going to be 1 over 4, right? And so on. So if you realize that if you sum this probability, the probability of getting 1 head plus the probability of getting 2 head plus the probability of getting 0 head is going to give you 1, and which is very good, because this one very important criteria of probabilities, the sum of the probabilities should be equal to 1. So the sum of the probability of a random event should be equal to 1, which in this fulfill that requirement here. You can realize that these are the possible outcomes that you can get from this experiment, and if you sum these probabilities, you're going to get up to 1, which is a very good sign. So that's what we have. And from this expression, we can draw the final conclusion by finding the probability mass function of this experiment. So we said that our variable of interest was x, right? So we was interested on finding how many head we observe in this experiment, and we realized that the probability of getting 1 head was 2 over 4. The probability of getting 2 head was 1 over 4. The probability of getting 0 head was 1 over 4. So basically, you can put it this way in the small table. So what you have here is the x, the possible outcome of your variable of interest. You can get 0, you can get 1, you can get 2, right? And this is going to be something like the probability of getting a p of x. So the probability of getting 0 head was 1 over 4. The probability of getting 2 head, I think, was the probability of getting 2 head was the probability of getting 1 head was 2 over 4. So this is 2 over 4. The probability of getting 1 head is going to be 1. Let me check the table. Yeah, so the probability of getting 1 head is 2 over 4, and the rest are 1 over 4. So 2 over 4 and 1 over 4, right? So this is the probability distribution of that. So basically, this is the table of probabilities, right? So how can you get the probability mass function from this, right? So basically, you define the probability mass function this way, because these are the p of x, which are the probability of this specific outcome. So this is the same as, you can just put it like f of x. And then from there, you can draw this definition of the probability mass function. So if you get 0 is the probability of that x equal to x. If you get 1 is the probability that s equal to 1. If you get 2 is the probability that s equal to 2. So this is how we define the probability mass function of an experiment, because this f of x represents the probability of the specific outcome. So the probability of getting 0 head is this number, the probability of getting 1 head is this, the probability of getting 2 head is this. And we can generalize that by saying that f of x, which is the probability mass function, so this is the probability mass function of the random variable x, which x in this case s represents the number of head that we observe in the experiment. So because we have that, you can represent the histogram of the probability mass function. So let's say we want to represent the histogram of the probability mass function that we just defined. So that probability mass function, this function was defined this way. We can just represent the histogram somewhere here. So at the same time, so we can visualize that. So if I pick that, this is the x-axis, this is the x, this is the y. I want to represent the probability mass function of this random variable. So so the first one is, this is 4, right? This is 2. Let me just put 2 here. And Okay, so this is basically, I just put it this way. So this is 2, this is 1, right? So the first number is 1/4, so 1/4 is somewhere here. I divide this by, this is 1/4, right? And the second number is 2 over 4, which is 2/4, so it's going to be somewhere here. Yeah, so this is 1/2, right? So it's going to be something like this. So what I can do is I can just represent the histogram this way, right? The center is at this point. And then oh, I did a mistake here. Sorry, I apologize. There's a small mistake here. So these are the x, these are the probability of x. So this is the probability. So this is the probability of x, right? So this is 0, and I'm just going to put this is 0, this is 1, this is too tight here. So let me put this for 1. So this is 1, this is 2, right? So these are the possible value of x, and on the y-axis we are going to put the possible value of y. So this is 1, this is 2, right? So the first one is 1/2. So 1/2 is something, because this is 1/4 is something here, right? This is 1/4. So I'm just going to come, because this is the first element is 0, so this 1/4, I'm just going to draw a small box here. That's the first one. So the second one is again 1/4 for the 2. So again at 2, this is 2. I'm just going to draw another box like this. And the last one is 2/4, which is 1/2. So it's somewhere here. 1/2 is somewhere here. So this is going to be, for 1, it's going to be something like this, right? So that's the probability mass function of this random variable. You can even expand it to make it closer, but I just keep it this way. So that's the histogram of that probability distribution. Now, and you can see that on the y-axis we have the probabilities, on the x-axis we have the possible value of x. So that's how you represent the histogram of a probability mass function. Now I give you another example here. This is another example. So we say that let f of x equal to x over c, and x is a random variable such that x can take the possible value of 1, 2, 3, 4. So find c such that f is a probability mass function. So what's the definition of probability mass function? F is a probability mass function if the sum of f of x equal to 1, 2, 3, 4 equal to 1. So basically is by definition the sum of the probability of an experiment. The sum of the outcome of the probability is going to be equal to 1. So in this case, if you compute the probability that f of 1, so the probability that the outcome is 1 is going to be 1 over c. F of 2 is going to be 2 over c. F of 3 is going to be 3 over c. F of 4 is 4 over c, right? So these are random experiment. And then if you sum the probability, the sum of the probability should be equal to 1. So basically you're going to be having 1 over c plus 2 over c plus 3 over c plus 4 over c equal to 1, right? So that means 4 plus 3 plus 2 plus 1 equal to C. So that means, and if you sum this is 4, 5, 6, 7, 8, 9, 10. So this is going to be 10 over C equal to 1, imply C equal to 10, right? So that's the value of the constant C, such that this is a probability mass function. Now, so now you have a f of x equal to x over 10. X equal to 1, 2, 3, 4. So these are the possible value of x. So that's the probability mass function that we find there. Now we can use the probability mass function to answer some questions. So I gave you that we find that f of x equal to x over 10. X can take the possible value of 1, 2, 3, 4, right? Now, what is the probability that x is less than 3, for example? So the probability of that of x less than 3 is the basically the sum of the probability of p of x such that x, or let me find it to write it differently. So this is the sum of the probability of f of x x less than 3, right? That's what it means. So basically this is going to be of f of 1 plus f of 2, right? Because these are the only value that we can have f less than 3. So this is going to be basically 1 over 10 plus 2 over 10, which is 3 over 10. That's the probability that we get there. So what about if I ask you the probability that, if I ask you what's the probability that x is less or equal to 5, then x less than 3, x greater than 3, right? So because when you look at this line, the possible value, we have 1, we have 2, we have 3, we have 4, right? Now what you see here is, and then we have 5. So we have to take this value, right? And we want x to be greater than 3. That means we don't want everything from this interval, so we only need this value, right? So basically is the probability that this equal to, so this is the same as the probability. So the probability that 3 less than x less than equal to 5 is the probability that x equal to 4 plus probability that x equal to 5, right? So which is basically f of x equal to 4 plus f of x equal to 5. Replace x by 4 and x by 5 in our expression, then we get the final result. The reason why we pick 5 is because this is included, right? And what you observe is, what I can do if I compute the probability that x less than 5, so I compute all these probabilities, right? And then I subtract the probability, this probability on that, I can still get the probability that of this probability, basically, right? But this is the easier way to go with this kind of expression. You break it down this way, it's most easier to visualize. So that's how you can use probability mass function to find some specific result. Now let us go a little bit down and get something here. Now we take another example here. We have let a random experiment be the casting of a pair of 6-sided dice, right? So we have a pair of 6-sided dice, and let x equal the minimum of the two outcomes. The goal is define the probability mass function and find the probability that the outcome is 2 or 5, right? Again, we said let a random experiment be the casting of a pair of fair 6-sided dice. So we have a pair of fair 6-sided dice, and let x equal the minimum of the two outcomes. So define the probability mass function and find the probability of the outcome that the outcome is 2 or 5. So before we start, look at what happened. We have here, so we have two dice. We have, if I call this die 1, and there are 6-side dice, this die 1, and die 2 also is 6-side dice. This is die 2, right? So we throw 2 dice, but our variable of interest is x is the minimum, so we want the minimum of the 2 outcomes, right? But because the 6-side dice, each dice have 6 sides, so we can have either 1, we can have a 2, we can have a 3, we can have a 4, we can have a 5, we can have a 6, right? So that's the number, the outcome that we can get. So because the minimum, these dice contain have a 6 faces, and each of them can be either 1, 2, 3, 4, 5, or 6. And the dice, if you recall, the dice is something, the face can be something like this, it can be something like this, and you get maybe that like this, or you can get something like this. In this side you can get something like 3, and so on. That's how the face of the dice are. That so you have 2 6-side dice, and you are interested on the minimum of the two dice. So what you can do to do that is you break that as a problem, single problem. So I call these 2 dice, I have dice 1 and have die 2. So what you observe here is so basically dice 1 is you get the possible value of this first die here, and the possible value of the second die there, right? So basically you get this table. All right, so that's what you have, right? So because each die have a 6 side, so you can have either one, the die can be 1, 2, 3, 4 up to 6. The second die is the same thing. So but the possible outcome, you can get either 1, you can get either 2, because let's say we pick this die, you have the minimum. So what you observe first is, let me use this. So these are, if you observe this is like the diagonal of this matrix. Now these numbers is the same, this one is the same as this, so we are just going to be interested on one side of the matrix, because if you pick both sides, you are going to do like the repetition. So these are our number of interests. We don't pick both sides, right? So that's the number that we are interested on. Now when you look at that, if you count how many numbers are yellow here, so we count this number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we have n equal to 21 numbers, right, that we are interested on. So the set of possible outcome is this set S. This is the set S, which is the set of yellow's number. So we can have this one, you can get the 2. So the minimum of 1 and 1 is 1, the minimum of 1 and 2 is 1, the minimum of 1 and 3 is 1, the minimum of 1 and 4 is 4, right, is 1. So basically these are the minimum. So basically you take the something here and you take another one here, you find the minimum, you put in the boxes, the intersection there. So these are the minimum, and because you can only pick the minimum once, because this, the minimum of 3, let's say I pick the minimum of 2 and 3 is the same as the minimum of 2 and 3 here. So this number and this are the same. So this and this, for example, is the same, the minimum, but I don't want to pick it twice, so that's why I just consider one side of the triangle, the upper bound of the triangle. So we have 21 numbers there. Now you have the 21 numbers there, and we can get the probability of each of them by just basically looking at the table. So if you look at what we have here, let's say the set of possible outcome is x equal to this set. So if you want to find the probability of getting x equal to 1, what you do is you just count how many of these yellow elements are ones, right? So you count, you're going to get this number. So basically you get 6 1. So n of 6 n of 1 equal to 6, n of 2 equal to 5. So basically this is the number of time that we get 1, this is the number of time we get 2. And to get the probability, you just divide by the total numbers. So basically we saw here that when you count the yellow numbers, we have 21 numbers, but if you count how many 1 we have there, you're going to have 6 1. If you count how many 2 you have in that table, you're going to have 5 6. If you count how many you're going to have if you count how many times you have a 2, we're going to have 5 times. So we divide 5 by 21 to get the probability of getting 2, right? So that's how we get these probabilities. It's very easy to get that. So you just basically count the cardinal, how many elements is specific, how many times a specific element occur in the table. Basically you interest on the yellow number. We don't want repetition. So that's how you get these probabilities. So this is on the top is the number of times that you get a specific value of x, and on the bottom you have the total numbers. That's how you get the probabilities. Now you can again define the probability mass function this way, and the probability of getting x equal to just the set of possible value. So basically f of x, which the probability mass function in this case again is the probability that s equal to x with x in this interval in the set 1 2 3 4 5 6. So this is the probability mass function of this experiment, and we can get all these probabilities. We saw how to find this. So that's the probability mass function. Now if you want to go further, again we can solve question like what's the probability that x is maybe equal to 4. You just basically pick the probability. What's the probability that x is greater than 6? So in this case, most of the time what you do is, because you don't want to spend time counting up to 6, you're just going to be saying that because it's the probability that x greater than 6 is the probability that x is less than 6 or equal to 6 minus 1, right? So basically what happened is, because the sum of the probability is equal to 1, what you do is, if you want the probability, observe this. So we want the probability that s is greater than 6. That means we want, no, we cannot get greater than 6 here. So if you want the probability that x is greater than 4, right? So basically I'm just going to explain you here. So the probability of x greater than 4 in this case is going to be a probability of x equal to 5 plus probability of x equal to 6, right? But in some cases you may have x equal to a set 1 and you have a lot of numbers, so it's a very long set. So what you do is, in order to find this probability, you have to notice that if I want to find the probability that s is greater than 4, what I can do is I can find the probability, because I know that the sum of the probability is going to be equal to 1. I can find the probability that x is, if I already had a probability that s less than that is equal to 1. So what I do is I said probability that x is greater than 4 equal to 1 minus the probability that s is less than 4. Is less or equal. So in this set, let's say we have 1, we have 2, we have 3, we have 4, we have 5, we have 6, right? So we had one probability that x is greater than 4. So basically we are interested on this number. So what I can do is the probability that is 1 minus probability that x is less or equal to 4, right? So that's how you get it. So because if you get these probabilities, right, the sum of these probabilities, so this sum s1 plus s2, it should be summed to 1, right? But if I already know this sum, I can just basically subtract 1 of that, then get this sum, right? So that's one technique that you can use, but this is very useful, especially when you are dealing with the continue case. This is very important trick that you have to know. Now we are going to discuss one specific example, one well-known experiment, which is the Bernoulli experiment. So in the Bernoulli experiment, it is a random experiment, right? So it's a random experiment. We saw what's the random variable. We only have two outcomes, success or failure. So in this case, you can classify success as maybe you select people and the outcome is, maybe you say if the outcome is a male, it's a success. If it's a female, it's a failure. Or if you say that you select some students from the class, if the student have a high IQ, you consider as a success, and if the student have a low IQ, you consider as a failure. You can also consider a test in the clinical setting, that if someone do the test and have the negative test, you consider as a success, and if you have a positive test, you consider as a failure. And the probability mass function of this kind of Bernoulli experiment is defined as follows. So in this case, this is how you define the probability mass function of the Bernoulli experiment. So in this, P is the probability of getting 1. So P is the probability equal to, so I'm just going to put it this way. So this is P equal to the probability that X equal to 1, right? If you consider 1 to be the probability of success, and the 1 minus P is the opposite. So that's how the Bernoulli experiment is. So the mean for the Bernoulli experiment is the mean, which is expected value of the random variable, is going to be P, and the variance of the random variable is going to be P times 1 minus P. And S is the outcome of selection. So that's what I was explaining here. For example, the probability of getting female, you can say that it's going to be 0, and or the probability of getting male is going to be probability of X equal to 1, something like that. And when you have a Bernoulli trial, when experiment is performed several times, independent time, we say that we have the Bernoulli trial. So the Bernoulli trial is a set of independent Bernoulli experiment. We call that Bernoulli trial. So now we want to pick one specific example here. Suppose that suppose that the percentage of American drivers who are multitasker is approximately 80%. So when you see a percentage like this, like 80%, this is a sign that this is a probability. And in a random sample of n driver, if S is the outcome of a sample, so that's it, we can have X equal to 1 for a multiple tasker and S equal to 0 if you're not multiple tasker. How is X distributed? So in this case, you can clearly say that S can take only two possible outcomes, 1 for the success and 0 for the failure. And we can tell that in this case, we only have two outcomes, success and failure. Therefore, this is a Bernoulli experiment, and this will be a Bernoulli random variable, right? S, how is S distributed? S is a Bernoulli random variable, and the probability in this case, the probability that X equal to 1, it is going to be, the probability is going to be 80%, right? Which is 0.8, right? And the probability that S equal to 0 is just going to be the opposite. It's going to be 1 minus 0.8, right? Which is going to be 0.2. So that's the second example is we select a random of 30 students. The probability of a random selected student is a boy is 60%. In this case, the random variable associated with the Bernoulli trial is defined as follows. So we can have that the probability that X is a boy equal to 1, and the probability that f is a girl is 0. So in this case, we say that if you get the boy, it's a success, or you can choose whatever. If you choose that the probability of getting a girl is a success, you say that the probability of getting s is a girl is equal to 1, and the probability that s equal the getting x as a girl is a 0. But in this case, I choose boy because I'm boy. I choose 0 for 1, and I choose boy for 1 for success and girl for failure. And I have nothing about this. It's just for explanation. So in this case, the probabilities is going to be of getting a boy, that x equal to boy equal to 60%, right, which is 0.6. And again, this is a Bernoulli experiment. That means you can basically write a probability mass function of this expression. So f of x in this case, we say that it's going to be p, so it's going to be 0.8. So it's going to be 0.8 to the x, and then 1 minus 0.8 to the 1 minus x, right? So with x taking the value 0, 1. So that's the probability mass function of that. And the way you see is, if x is 1, for example, you replace 1 here, you're going to have a 1 minus 1. This is going to be 0, just going to be the probability that you get the boy, which is 0.8. That's one interesting fact. So it's what I'm saying here is this: if you have the probability mass function, so you have f of x for a Bernoulli experiment, you have p, you have x, this is 1 minus p, and you have 1 minus x, and x take the value 0, 1, right? So we say that this is the probability of getting 1, and this is the probability of getting 0. So this is the probability of getting 1, this is the probability of getting 0. And the way you can figure out here is that if you replace x by 1 in this expression, so if you say f of 1, it's just going to be p, and then 1 here. You have 1 minus p, then 1 minus 1. So this is going to be 0, so this gives you p, right? And if you do the opposite, you're going to get 1 minus p. So that shows that indeed this is the probability of getting 1, and this is the probability of getting 0, and the probability mass function is indeed well defined. And you can do the same thing here for the Bernoulli trial. You are just going to replace the equation by the probability that you get here, and you are ready to go. The second one is, so you identify that for this experiment you can have either success or failure for the random variable of interest. So our variable of interest is here whether it's a boy or a girl. So that's the trick, how you figure out that's the Bernoulli experiment. Another example here is suppose that the probability of generating a good seed is 0.6, which is a succeed. If you generate 15 seed and assume that the generation of one seed is independent of generation of another seed, this corresponds to 10 Bernoulli trial with probability p equal to 0.8. Again, our variable of interest is x here, is either the seed succeed or not. So the seed succeed or failure, right? So again, this is a Bernoulli experiment because the probability that x equal to succeed is, in this case, is 0.8, right? So it's, again, this is a Bernoulli experiment because we see that our variable of interest is either the seed succeed or a fail. Now we are going to check something that we call the Bernoulli trial, the binomial trial. So the binomial experiment, the difference is that in order to figure out whether you are dealing with a binomial experiment, so first each individual experiment should be a Bernoulli experiment, and you do a sequence of Bernoulli experiments to get a binomial experiment. So what here is, we say that we are interested on the number of occurrence in n Bernoulli trial, right? So again, you see that we are using the Bernoulli trial, Bernoulli experiment, Bernoulli trial here, but we do a series of Bernoulli trial. But our interest is how many times in the series of Bernoulli trial we have a success. So we are interested on the number x of success in n Bernoulli trial. So s is equal to, you can have zero Bernoulli trial, so that means you have no trial at all, or you can do one Bernoulli trial and get a success, or you can do one Bernoulli trial, two Bernoulli trial, three Bernoulli trial, and every time you get a Bernoulli trial, you count how many times you have a success there. That's what we have a binomial experiment. So the way you see this is just like you do a series of experiment, of independent experiment, and each experiment is a Bernoulli experiment, and at the end you are interested on how many times on those experiments you get a success outcome, and that is a binomial experiment. So that's how it is defined, and the probability mass function of a binomial experiment is defined this way. And where again x is p is the probability of success, and the variance is np times 1 minus p, and the expectation, which is the mean, is np, right? And we usually use this notation for a binomial experiment, right? So we have the trial are independent. We have a sequence of independent Bernoulli trial and Bernoulli experiment, and we are interested on how many times you get a success on those experiments. So let's say one example here. Suppose that the percentage of American drivers who are multitaskers is approximately 80%. In a random sample of n driver, n equal the number of multiple taskers. How is x distributed, right? Now s here is the number of multiple taskers. Now look at this, it's the same problem as the one that we had here, but I just changed the way. In this case, s is the sample of driver, s is the outcome. So in this case, you see that x is the outcome. That said, we can get either multiple tasker or not multiple tasker. So it's a binomial. We can have a multiple tasker or not multiple tasker. It's a Bernoulli. Now here the question here is s equal the number of multiple tasker. Initially it was the same problem we was asking. The question is the outcome was our value interest was either are you multiple tasker or not. But now you want the number of multiple taskers. So it's like in the independent Bernoulli trial. So we do a Bernoulli trial. We select a student. We say that it's a multiple tasker or not. We select another one. We see that it's a multiple tasker or not. We select another driver. We see it's multiple tasker or not, and so on until we get a 20 driver. But our interest here is how many times on those selection the driver was multiple tasker. So that's why we say that this is a Bernoulli experiment, a binomial experiment. It's a series of Bernoulli experiment, and in every Bernoulli experiment we can get either multiple tasker or not multiple tasker. Now we do that so many times, and we count how many times you get the multiple tasker. That's our interest. So this is it's a Bernoulli, a binomial experiment, and it's a series of independent Bernoulli experiment. So this is a binomial. So how is x distributed? So this is a binomial distribution. Find the mean and the variance of x. So in this case, the probability p. So in this case, we just get in this case our p equal to 0.8 again, but the difference is the equation, the probability mass function here is f of x equal to so it's going to be n choose n choose x. So it's going to be this equation basically, and we have that p in this is going to be 0.8, right? So we just replace p by 0.8, and n in this case is going to be, I don't want to copy that, n was n was 10, right? So n was 10. N was 10. So you just replace n by whatever you have here. So this n is the number of sample that is selected, right? So you just replace n by 10 in this case. So you have n equal to 10, right? And you can have the mean, which is given by this. You have the variance, which is given then by this. So that was a binomial experiment. I think that's what we have for today. And if you have a question, feel free to post it, so we discuss. So I'll give you more explanation about that, and you can post on the comment. Thank you, and see you on the next video.